Thank you. So thanks to the organizers for the opportunity to tell you a bit about our work done with Andrea Guerrieri that just gave us a beautiful talk, and Pedro Vieira on trying to incorporate some multi-particle scattering amplitudes in the S-matrix Bootstrap and use that to study confining flux tubes in pure-Yang-Mills theory. And as a way of motivation, wait. Yeah. Okay. And as a way of motivation, let me start by celebrating the successes of a different type of bootstrap. So let me remind you that by now, the conformal bootstrap has evolved into this framework that allows us to essentially or effectively solve many generic non-perturbative conformal field theories in arbitrary dimensions. And by effectively solve here, I mean that it allows us to sharply bound the most relevant observables in these quantum field theories. So for example, we recently released this study of the Ising CFT in 3 dimensions, where we consider the bootstrap system of 4-point correlation functions of the spin, energy, and stress tensor operators in this theory, which allowed us to determine the scaling dimensions and the structure constants of these operators to 9 digits. So in a sense, the conformal bootstrap allows us to do precision physics in these strongly coupled conformal field theories. Now, in the presence of mass scales, quantum field theories dynamics can become much more complex and much richer, and we still seem to be far from effectively solving such theories in the sense that I just described. However, in theories that admit scattering observables, a strategy that has been adopted to try to repeat the success of the conformal bootstrap has been to try to place bounds on the dynamics of observables by requiring that the 2-to-2 S matrix is consistent with fundamental principles such as causality and unitarity. Now, there have been many successes in this direction. For example, on bounding effective field theory coefficients and on-shell couplings in hadronic physics, bounds on effective field theories of gravity, constraints on the outcome of RG flows. So you start with some UVCFT, you deform it, you land on some massive phase, you study scattering in this phase, and you constrain the dynamics. Or, for example, discovery of new exactly solvable S matrices in 2 dimensions. And this program is, of course, the S-matrix Bootstrap. And today I want to discuss the inclusion of end-to-end processes in the Bootstrap. So given all these successes of the 2-to-2 Bootstrap, we should ask why we should really consider multi-particle amplitudes and not just keep pushing 2-to-2 more and more. And perhaps the best motivation I can give you is that often particle production is the dominant outcome of scattering processes. And by considering only 2-to-2 processes, we are not properly capturing the dominant physics. This is the case, for example, in gravity theories, where in many kinematical regimes, the scattering is dominated by emission of gravity waves, or it's also true, for example, in colliders. Now, you might say that if your goal is just to develop the framework starting with a gravity or a standard model might be too complicated, so you might want to try to develop the framework first in some simpler systems. But I want to argue that even in some of the simplest non-perturbative quantum field theories you can imagine, particle production is often dominates. So for example, let's consider the 2-dimensionalizing model at high temperatures and small transverse magnetic fields. This is one of the simplest field theories you can imagine. We start with the simplest minimal model in 2 dimensions. We deformed by the temperature operator and then by the spin operator. The first 2 terms just give massive free fermion. The mass scale is given by the tau parameter. And then we do a small deformation in the spin direction. So we have a theory that's very close to being free, yet Zamolodchikov has long conjectured that particle production dominates scattering processes in this theory at high energies for arbitrarily small magnetic field. And this has been recently observed in some beautiful real-time simulations with tensor network models, where these authors observed complete inelasticity of the scattering process at high energies and arbitrarily small magnetic field. Now, there are many other motivations to study N2M. For example, they directly expose many properties of scattering amplitudes that are not accessible from 2-to-2 alone, such as soft theorems, factorization, and cluster decomposition. However, today I want to discuss a more concrete and quantitative motivation to study these processes, which is the following. So let's consider what's arguably the simplest Bootstrap question one could ask. Let's start with a massive quantum field theory in 2 dimensions with a single stable particle phi of mass m, and ask the following question. How big can the on-shell cubic coupling G phi 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 of these particles be in units of the mass m? Now, I'll show you it's actually not so easy to answer this question, but you can give a preliminary answer and use unitarity, crossing symmetry, and analyticity of the 2-to-2 amplitude to place a bound on this cubic coupling, and you find this result. Now, it turns out that we know the unique 2-to-2 amplitude that saturates these bounds, that is, that realizes this cubic coupling equal to this value. And here is the answer. So let's examine this optimal unique S matrix in more detail. So recall we are in 2 dimensions, so there are no angles. The only variable is the energy. So for example, the other 2 Mandelsons are fixed. U equals 0 because we are always in the forward limit in 2 dimensions. And T is 4m squared minus S. Now this amplitude satisfies all we could ask from a 2-to-2 amplitude, namely it's unitary. In particular, it's a pure phase for physical kinematics. It's crossing symmetric under S and T exchange. And it's analytic where it needs to be. In fact, its only singularities are the unitarity cuts and the cubic exchanges. And you can compute the residue of these cubic exchanges, and you'll find this optimal value here. So it seems that from 2-to-2, the game is over. We found an explicit S matrix that satisfies all the basic axioms and realizes this optimal bound, which has been derived with rigorous methods. However, I'm going to argue that there is no quantum field theory that realizes this value, and that this S matrix is actually inconsistent. And to do that, we need to examine multi-particle amplitudes. So let's consider 2-to-3 amplitudes in this theory. Generically, 2-to-3 amplitudes will have singularities, and in particular, it will have singularities in the collinear limit where the incoming momenta P1 is equal to the outgoing momenta P3. The singularities come from 2 related on-shell processes or diagrams. Namely the single particle exchange and this triangular on-shell diagram where all the internal lines are on-shell. Now, in 2 dimensions, these 2 diagrams actually correspond to poles in the S matrix, and the residues are as such. So the single particle exchange has a residue proportional to the cubic coupling times the S matrix evaluated at Mandelstam S12, while the triangle diagram has a residue that's proportional to the cubic coupling times the S matrix 2-to-2 evaluated at Mandelstam 1,4, and then the S matrix evaluated at Mandelstam 1,5. Now, I'm soon going to argue that unless this residue cancels, there is a contradiction. However, this residue can only cancel if the S matrix satisfies this equation, and the optimal S matrix from the last slide does not solve this equation. So now I'm going to argue that this is a contradiction. Well, if the residue does not cancel, this means that the 2-to-3 amplitude has a pole, so it cannot be 0. If this amplitude cannot be 0, then the probability of 2 particles going into 3 particles is not 0, which means that the probability of 2 particles going into 2 particles is strictly smaller than 1, which means that S optimal cannot be a pure phase, but it is. So it's a contradiction. So we've concluded that this S matrix is excluded, there's no consistent quantum field theory with this S matrix or this cubic coupling. So even for this very simple S matrix bootstrap problem, we see that the multi-particle consistency should play an important role. So our goal today, to develop a general bootstrap framework for multi-particles is very challenging because these objects are very complicated, non-perturbatively. So our strategy today will be to look for the simplest setup, which allows us to impose some form of analytic unitarity and crossing for multi-particle amplitudes. And fortunately, we do not need to consider a very boring system. Still, we can do some very interesting physics. So the context in which we'll develop this is in confining strings, so QCD strings. So our goal is to constrain the dynamics of color flux tubes in pure Yang-Mills theory using multi-particle S matrix bootstrap techniques. So let's consider some long flux tube, for example, in pure SUN Yang-Mills theory in 3 or 4 dimensions, which you can imagine are sourced by considering a theory in a cylinder, wrapping some pair of Wilson loops around the compact dimension of radius r, and then taking the radius r to be very large, so we are back in flat space. Now there's a flux tube in between the Wilson loops. And the low energy excitations on top of this flux tube are massless. They're nothing but the transverse modes of the strings, or if you want, the Goldstone bosons from the breaking of the Boak-Poincare symmetry due to the presence of the long string, which breaks the Boak-Poincare into Poincare along the word sheet and transverse rotations. Now we'll focus today on d equals to 3, so there is a single Goldstone mode, but we could easily generalize everything to d equals 4 by tracking the flavor index of the pair of Goldstone modes in d equals 4. So we'll consider the dynamics of these Goldstone modes on the word sheet, and this low energy dynamics is governed by the effective field theory. And we can write this effective field theory by reminding ourselves that the action must be invariant under Boak-Poincare, and so it can be given by an expansion in curvature invariance. So here's the first few terms in this action. So the leading term is just the Nambu-Goto action, just measures the area of the word sheet, and then there are higher corrections in terms of Ricci and extrinsic curvature. Now, this is an expansion on energy times the string length, which is essentially inverse confinement scale. And then the leading term is Nambu-Goto, as I just said, and there are higher terms. So we have a weakly coupled low energy theory. However, at energies of order 1 over string length, the effective field theory breaks down and the theory is strongly coupled. And our goal is to constrain physics in this regime. So, and we will do so by considering scattering Goldstones on top of the flux tube, as these authors first initiate. So, however, this proposal should raise alarms. So I'm suggesting considering the scattering of massless particles in 2 dimensions. And you might argue that, well, amplitudes should be plugged by infrared divergences, and the S matrix perhaps not even a good observable. And even worse, so we are in 2 dimensions, so massless particles are either left or right movers. So you can imagine you have a bundle of, say, right movers. They'll just be moving collinearly forever. They never separate. So you might even question whether they define good asymptotic space, a good asymptotic Fock space if these particles never stop interacting and never separate. So let's consider these problems. To examine these problems, let's consider a bunch of isolated right movers. And let's consider their self-scattering. So the S matrix element where we only have right movers. Now, Poincare invariants tell us that this S matrix, well, boost acts on the momenta by just rescaling. And so Poincare invariants tell us that this S matrix depends only on ratios of the momentas. However, ratios of momenta are energy scale independent. So by symmetry, we can evaluate this S matrix at any energy scale we want. In particular, we can evaluate it at low energies. But at low energies, we can compute everything in terms of EFT, which is expressed just in terms of derivatives of the transverse field. In other words, the Goldstones are derivatively coupled. And so the theory is free at low energies. However, again, by symmetry, if it's free at low energy, it's free at every energy. And so we conclude that the right mover's S matrix is trivial. And so as a consequence, there's no issue with having these particles that move collinearly forever. They define a good asymptotic Fock space. And the S matrix is, in fact, well-defined and free of infrared and collinear divergences. And these statements can be backed up by explicit EFT perturbation theory computations. Okay, so summary is that right-right scattering, equivalently left-left scattering, is trivial. And so now we can discuss the actual non-trivial part of the S matrix, which is the left-right scattering. So we'll be considering this a multi-particle process. Let's discuss first some kinematics. So we'll consider incoming right-moving momenta, PR, the total right-moving momenta. And let's say that they're divided among n incoming right movers. Same story applies for left movers and for outgoing particles. Now, we'll parameterize these n incoming right movers by the total momenta PR and their energy fractions, beta 1 to beta n. Meaning, the first particle in this bundle has momenta P1 is equal to beta 1 times PR. There's an R missing here. And for physical configurations, we must have that the sum of the energy fractions sums to 1, and they're all positive. So our strategy will be to consider the scattering of certain jet states. So we define a jet state by integrating this plane wave basis against the wave packets in the energy fractions. Now, it's easy to write a complete basis of discrete wave functions that parameterize the full Fock space in this way. And let me emphasize, this is just a change of basis. We're not losing any information. We capture the full asymmetric as physical kinematics by going to this basis. Now, these wave functions can be chosen so that, and normalized, so that their overlaps is given just by this expression, which are just like one particle massless states overlaps. And in fact, kinematically, these states, they transform just like one particle states under Poincaré. So you can imagine, like under Wigner classification, you'd even say that they are one particle states, only that now they carry this essentially infinite dimensional flavor index, which label this wave function inside these jets. So from this argument, you might expect that the 2-to-2 amplitudes of these jets should satisfy the same analytistic cross-section unitarity properties of standard 2-to-2 amplitudes of individual Goldstones, only that now again you need to treat this wave packet index as some new flavor index. So this is the main idea that will allow us to do multi-particle bootstrap in this two-dimensional setup. Now, let me emphasize that by imposing crossing analyticity of these jet amplitudes, we're imposing some, but not all, of the crossing analyticity properties that you might expect of the full N2M S matrix. In particular, we are exploring analyticity in the total energy, but not on the energy fractions. And we are exploring crossing moves where we cross all left movers or all right movers at once, but not individual components inside the jets. However, we are capturing full unitarity of these amplitudes because, again, we're just doing a change of basis. Okay. Now, I'm going to discuss an explicit computation. So we'll do actually numerical bootstrap to obtain bounds on the dynamics. And to do so, we need to consider a finite system of amplitudes so we can put in the computer. So we'll consider amplitude made out of the two states, namely the single particle state of a single Goldstone and this two particle state given by integrating the two particle state against this wave function. And then we build all the 2-to-2 S matrices out of these two new one particle states, which are equivalent to the 2-to-2, 2-to-4, 4-to-4, 3-to-3 transmission, and 3-to-3 reflection amplitudes, where we should remember that in these blue lines, in these multi-particle amplitudes, we are projecting against these wave functions here. And we do not have 2-to-3 or 3-to-4 amplitudes because we have essentially parity symmetry in space-time, which implies that the Goldstone are Z2 odds, and so these amplitudes vanish. Okay, and of course, in the future, one can consider bigger systems with more and more external jet states, and there's no abstraction other than computational ones. So with this posed, the standard constraints take the simple form. So for example, crossing symmetry, just a bunch of linear relation between these amplitudes. Unitarity become simple semi-definite constraints on these amplitudes. And analyticity takes the usual form of simple single variable subtracted dispersion relations, which we can impose numerically. Now, with these constraints, we can now ask about bounds on various observables. And I don't want to emphasize the numerical methods. For those that know, you can use primal methods, dual methods. They give effectively the same answer. For those that are not familiar with these methods, you just assume that everything is done analytically, which is approximately true. And so we can now discuss what observables we bound on these systems. And so for that, let's recall our goal. Our goal is to understand the dynamics at energies of order inverse string length. So a natural set of observables to consider are effective couplings defined by evaluating these jet S matrices at some energy scale S star, and which in the upper half plane where the S matrix is analytic. And then these observables can then be expressed in terms of physical values of the S matrix through dispersion relations via some sum rules. So for example, we'll consider the allowed place of 4, 8, and 6 particle couplings defined by evaluating these S matrices at S star, which we take to be I over string length squared. So what values can X, Y, and Z take, these affected 4, 6, and 8 particle couplings? Well, if you only impose analyticity, unitarity, and crossing of this system, you get that they must live in this blue solid. So here the axes are between -1 and 1. And this is a very generic bound that should apply to any massless two-dimensional theory for which the S matrix is a good observable. But then we can start to impose some actual flux tube physics. So for example, we can impose the leading EFT constraints, namely that the amplitudes should be given by the Nambu-Goto action up to order S squared in energy. They are universal. Any quantum field theory with this EFT should behave in this way. And if we impose this constraint, which again you can imagine is done exactly, you find that these effective couplings must now live in this red solid, which is 100 times smaller in volume or 5 times smaller in linear dimension than the blue surface. And so this result suggests you a strategy. Let's just impose more and more EFT to higher and higher orders, and then the bounds will shrink, and then we're going to celebrate. So let's compute higher order EFT. So we so far consider the constraints coming from the Nambu-Goto action. Now, the next few terms in the action are the Ricci term, which is actually a total derivative, and then this term is vanishes on shell. So corrections to scattering amplitude come only from the k to the 4 term. And in fact, all S matrices are parameterized by a single gamma parameter, which is the coefficient of k to the 4 up to order S to the 4. So for example, the 2 to 2 S matrix takes this form to this order. And we can impose these constraints. And we learned that this idea fails. It turns out that these bounds on X, Y, and Z are not affected by imposing EFT to higher orders. However, they fail in an interesting way. We learned that as we impose more EFT, the S matrices that saturate the previous bounds, they must have very large Wilson coefficients, which means that the EFT is breaking down at arbitrarily low scales. This is very unphysical. In fact, physical theories of interest have very small values for this parameter gamma. For example, lattice QCD has measured this parameter gamma in SU2 and SU3 theory, and they are order 1/10. So this suggests looking for bounds on these effective couplings, assuming that gamma is small. For example, gamma smaller than 0.7 includes the lattice constraints. And you find that, well, for those that are familiar, this is similar in philosophy to imposing a gap in the conformal bootstrap to isolate theories of interest. Now, if you do so, you learn now that these effective couplings must live in this very tiny green island, which is 100 times smaller in linear dimension compared to the red surface. So now we can determine these effective couplings to 3 digits. So a way to interpret this S matrix bootstrap results is that we are now able to determine this finite energy S matrix observables with small error bars, given minimal assumptions, given the minimal physical input of small effective field theory coefficients, which we learned from lattice. Now, not being limited to just 2 amplitudes, these confining flux tubes seem to be the simplest S matrix bootstrap setup we can consider. And so the dream here is that we can go all the way and effectively solve the dynamics of the strings in confining gauge theories using bootstrap techniques, much like we did in conformal bootstrap. And of course, this is a very hard problem. We should impose all other physical constraints you can think of. So here are some pressing questions that I'm mostly interested in. How does asymptotic freedom reflect on the physics of flux tubes? What role does open-closed duality play in these confining strings beyond the EFT regime? And how to systematically leverage the large amount of bulk lattice data we have to systematically constrain the worldsheet dynamics? Since so far, we only imputed the magnitude of the leading EFT coefficients, which proved to be a very powerful input. So these are work in progress with my awesome collaborator, Jan Albert, and we should report it in the next few months. But overall, the goal is to try to turn the problem of solving the worldsheet dynamics of Fourier-Mills theory into an experimental one, where by experimental I mean lattice, and try to fix the S matrix in this theory using purely lattice plus bootstrap techniques. Now, the success story from 2 to 2 pions, see, for example, the talk at Amplitudes last year by Ife, plus the simple kinematics of the confining string S matrix, which allow us to control multi-particle processes give us hope that this might be possible. Thank you.